W minus Z naught I am taking here. Where we are taking here, where W belongs to G, W not equal to Z. W belongs to G and W not equal to Z. So where we have taken here Z of Z naught here, so that is F dash Z naught. G naught G Z0. That is the first derivative we are taking F dash of Z naught I am taking here. But even though we are taking here, then G is a continuous, then G is continuous on G, and analytic analytic on G, we are taking here G minus Z naught. So we are taking from the earlier ones also. What is the G minus Z naught? So the earlier one, what we have taken here in the earlier theorem, Cauchy's theorem of the convex test. So therefore, the Cauchy's convex test, what is the convex set? Let VA be open. Let V stands to Q is a continuous on V and we are taking V minus Z naught, where Z naught belongs to V. In a triangle gamma and the interior contained here, integration of gamma fz dz is equal to 0. So convex of the set, then integration of gamma fz dz is equal to 0. The closure path is the closure path in gamma in V. So is a closure path in gamma in V we are taking here. So that is the condition of that one. That one I am taking here. The integration of the Fw by W minus Z naught dW I am taking here. That is F of Z naught. So F of W means F of Z naught by W minus Z naught of dW I am taking here is equal to, I am taking Fz naught is a constant taking outside gamma dW by Z minus Z naught, that is equal to 2 pi. So where I am taking 2 pi Z naught. So taking one diagram here. This is the one diagram. This is not a diagram. I'm taking the diagram here. Just a minute. I'm taking the diagram taking here. Just a minute. I'm taking the diagram here. Okay. This is not showing here. It's not showing here. I'm just I will do that. Draw the diagram here. This is one circle, a not exact given circle here. This is a circle. This is a, just a minute. We are taking the insert. I'm taking the pictures. So this is I'm taking here. This is one the circle. This is the one circle I'm taking. This is the one. So this is the center of this one. I'm not removing here. This is L0. This is H. This is L1. This is A. This is the A I'm taking here. This is J. This is C. This is B. This is A I'm taking here. So this is the E and D. This is the circle of L0. This is D. So this is L2. This is I'm taking L2. K. This is R. This is K. This is R I'm taking it. This is H already I told you. HL1. So the above in this one I'm telling here the left gamma one. The Jordan curve. What is the Jordan curve here? I'm writing it A B C D E H A. See here A B C D. Where A here? where A is the top of the bottom, A to B, A to B, A to the cycling rotating here, A, B, C, D. So A, B, C, D, off of the center of the point, A, B, C, D, E, then H, A, then A, B, C, D, A, B, C, D, E, H, A, B, C, D, E, H, again A. So this is the E, H is the both sides that we are taking E, B, C, D, H, that is center point I'm taking here. And gamma to Jordan curve, we can take again the C. We're taking here C, J, C, J, A, H. Again C, J, A, H. This is a one center of point, C, J, A, H, A, H, K, D, C. This is in the Kundu, we are taking EH, now KD, the KDC. This is the second point. So our first center point taking that A, B, C, D, E, H, A. The second center point is C, J, A, H, K, D, C. So the rectifiable Jordan curve enclosing the simply connected domain here, not containing the Z naught we are taking here. Even though we are taking here, assuming the Cauchy theorem, such domains we can get the integration of f of w by w minus z naught of dw is equal to 0. That is gamma 1. That is gamma 1 I am taking here is equal to 0 I am taking here. That is f of w by w minus z naught dw. So this is also integration of gamma 2. So f of w by z minus z naught dw integration of gamma to fw by w minus z naught. This is equal to 0 for it follows immediately that immediately what we are taking here in integration of R integration of R f of w by w minus z naught of dw, then integration of L f of w by w minus z naught dz. Noting that the integral of along L1 and L. L1 and L2 what means that A, B, C, D, E, H, A, C, J, H, K, D, C. And so L1 and L2 cancel, each being traced in the twice along the opposite directions. So this is the condition of the Cauchy integral is equal to 1 by 2 is equal to 0 we have taken. Some examples we have to take here. See one example here on this one. Evaluate integration of gamma or z plus 1 by z dz where gamma is given by gamma t, that is cos theta plus I sin theta, that is 60 cos theta plus I sin theta 0 less than t less than 2 pi I'm taking here, 0 less than 2 less than 2 pi I'm taking here. So integration of gamma z plus 1 by z into dz is equal to integration of gamma z dz is equal to, I'm separating z dz and gamma dz. So the 1 by dz means so that is dz by z also we can write here dz by dz. So since G is analytic entire, G is gamma is closed in a counter set already told in G. So therefore integration of gamma z dz is equal to 0. So therefore integration of gamma z dz is equal to 0 is a counter set. So therefore also 0 is the center of the gamma. So we can take the belongs to that is I of gamma and B by Cauchy's integral formula we know that integration of dz by dz is equal to 2 pi I. That is a gamma. So therefore, hence integration of gamma of z plus 1 by z is equal to dz is equal to 2 pi. Why means you know that integration of z dz is equal to 0, but dz by the Cauchy integral from the 2 pi I. But here f of z is equal to 1 and f of 0 is equal to 1 we are taking here. So in that condition, so therefore z plus 1 by z dz of integration or z plus 1 by z dz is equal to 2 pi, the condition is satisfied here. Then another one problem, evaluate integration of our 3z square plus 7z plus 1 by z plus 1. So by dz, where dz, where gamma of z plus 1 is equal to 1. So the integrand can be written as the integrand can be written as we are taking here. First, we are taking here 3z plus 4 minus. So this is simplifying. As I am simplifying, this is 3z plus 4 minus 3 by z plus 1. So that means 3z square plus 7z. So this is a simplification of, so that we are taking here integration of gamma 3z square plus 7z plus 1 by z plus 1 dz. That is a simplification I am writing here. It is integration of r 3z plus 4 Again, minus of the integration of gamma dz by z plus 1. So dz by z plus 1, I'm taking here for the easy of equation of the formula, the first integral domain. So we are taking here the first integral domain. The first integral domain. First integral domain I'm taking here, integral taking here, integration of gamma 3z minus 4 is equal to 0. Why? Because by the Cauchy's theorem, we know that here, by the 3z minus 4, we have to 0 here, 3z plus 4, sorry, 3z plus 4 is equal to 0. By the Cauchy's theorem, earlier one, by 3z plus 4 is analytic and gamma is a closure contour. Gamma is a closure contour. 3z plus 4 is equal to 0. We know that here. Now we can take that here. Again, take the diagram here. This is the center point. We're taking here, this is 1, 0, comma, minus 1. So by the Cauchy's integral theorem, again we know that 3z plus 0 is equal, again the only one integration part here left, dz by, what is the z of minus 1? I'm taking it z of minus 1. That is dz by z plus 1 is equal to 2 pi I. So earlier one also we can take that z dz by z is equal to 2 pi I. So minus, so dz of, that is also f of z is equal to 1, f of minus 1 is equal to 1, f of z is equal to 1, f of minus 1. So at the point minus y here, f of z is equal to 1 and f of minus 1 is equal to 1. So that point minus 1 lies in the I gamma. So therefore integration of gamma 3z square plus 7z plus 1 by z plus 1 is equal to dz equal to 2 pi I minus 3. 2 pi is equal to minus 3. So 2 pi, where is 2 pi I? That is the integration of dz, z minus 1, that is the 2 pi I. Then 3z plus 4, that is a contour, therefore minus 3 is equal to, that is minus 6 pi I, this is the value, 6 minus 6 pi I we are taking here. That's one problem we are writing here. Another one, determine the value of z plus 4 by z square plus 2z plus 5, where gamma is modulus of the difficulty. So integrand analytic expiry everywhere, sorry, analytic everywhere except the points which is dominated the variance here. So I'm taking that wall call this thing. So I'm taking the one diagram. Zero minus my one two minus one two minus one. I2 minus I2 minus I. This is 1 2 minus 1. Minus 1 0 1, that is the center point, that is the x, this is the y, this is the y. So in the by the Cauchy theorem, we know that again the Cauchy theorem in the contour also, integration of z plus 4 by z square plus 2z plus 5 into dz is equal to 0. So therefore z square plus z plus 4 by z square plus is analytic inside and gamma is here. So therefore the value is 0 we are taking here. These are fundamental problems in this one. So many. So many worked out exercises here. Then we can go the another one problem. That's the consequence of Cauchy's theorem. Consequence of the Cauchy's theorem. Consequences of the Cauchy theorem. Consequences of the Cauchy theorem here. So let F be analytic one theorem. In the Cauchy sequence, what's the Poisson integral lemma? Livolli's theorem we can learn here in this and solve the problem. Solve problem here. One theorem we have to learn here. So let F be a, let F be analytic on the disk ER alpha, center of alpha, center of alpha and the radius r, center of alpha and the radius of r. So let C1 the circle. Let C1 be the circle. Let C1 be the circle. Z minus alpha is equal to Z minus alpha is equal to rho less than n. So in the modulus of Z minus alpha, I'm taking here. So then the any point, what if you are taking in the Z naught here? Then any point I'm taking here in d P alpha, we have f of Z naught 1 by 2 pi I C1 f of Z by Z minus Z naught of beta. Z minus Z naught by beta we are taking here. Also, if Z naught does not belong, so it does not belonging to D alpha belongs to dp alpha, they can take here. So what is the condition? 0 is equal to 1 by 2 pi. We know that C1 f of Z by in the Cauchy theorem, we know that here that is Z minus Z naught by dp1 that is 1. So Cauchy's integral theorem multiplication of the constant domain also we learn here. A characteristic feature of Cauchy's integral formula can be represented as Poisson integrals here. Then another one theorem we have to learn here. If f is analytic on a domain G and if G contains the circle CP, that is Z minus Z naught is equal to rho, and its interior we are taking here f of Z naught is equal to 1 by 2 pi 0 to 2 pi f of Z naught plus P into e power I theta into d. Z naught plus P into e power I theta d theta. There is the value of the f at the Z naught is equal to average its values on the circle CP, the center Z. So we can write here the value of f at the point Z naught equals the average of the values on the circle CP with center 0, with center Z naught I'm taking it. If I'm taking the equation of the circle, the equation of the circle, the equation of the circle is CP is equal to right here Z into Z naught plus rho into e power I theta. So 0 less than or equal to theta less than or equal to 2 pi. 0 less than or equal to theta less than or equal to 2 pi. So therefore, from the Cauchy's integral formula, we know that here f of Z naught is equal to 1 by 2 pi I integration of Cp, that is f of Z by Z minus Z naught. Dz I am taking here. So 1 by 2 pi I 0 to 2 pi f of Z naught plus rho into e power I theta into rho into e power I. So what we are taking in place of integration of 0 to 2 pi, I am taking here. So f of z is equal to z naught plus rho of I theta into rho of I theta by into again I am taking here I into rho of e power I theta d theta. So 1 by 2 pi integration of 0 to pi f of z naught plus rho into e power I theta d theta. Rho into e power I theta d theta. So the condition has been satisfied here. Where we are taking integration of 0 to 2 pi. 1 by 2 pi I am taking these values are substituting in each one. So therefore f of z naught plus rho into I power d theta d theta. These values are coming here. So therefore hence the theorem. Then another one theorem we have to run here. Let f be analytic taking a region G, then F dash Z, F double dash Z, F N Z. So therefore F and Z all exist in G and are analyzed. In G are analyzed. So see here, given any point alpha and G, given so the proof given any point we are taking here alpha of G, given any point of alpha of G, I'm taking here. So we can prove that function f of Z has derivatives of all orders in alpha. We can prove that the function f of Z has derivatives of all orders at alpha. Of all orders at alpha. So we have to assume that here. So we can take assume here. Gamma of y z minus alpha is equal to r. Z minus alpha is equal to r. To be sufficiently to be a sufficiently small circle completely contained here. Small circles completely contained in G what we are taking here. So therefore then for any point Z naught, then for any point then for any point Z naught, inside we are taking here inside gamma r. So therefore we know that the Cauchy integral formula is here. What is the Cauchy integral formula? F of Z naught is equal to 1 by 2 pi integration of gamma. So f of Z by Z naught, Z minus Z naught is what I'm writing here. F of Z naught is equal to 1 by 2 pi gamma f of Z by Z minus Z naught of dz. This is the first equation. So we are derivating this equation n times. N times means one in place of one. What we have to came here n dash. So we have equation one derivates differentiating or derivative derivative first equation derivative n times with respect to z naught. With respect to z naught, we can expect that f of n z naught we are taking there n factorial by 2 pi I. The integration of gamma for f of z by z minus z naught n plus 1 dz. This is equation. So nth function I am taking here. So in the nth function I am taking in place of 1 n factorial, I am taking here f of z by z minus z naught whole power n plus 1. That is also n plus 1 we are going here. This is the equation number. This is equation number 1. This is equation number 2 we are taking here. So therefore, in this one, about the equation 2 formula, induction is induction by the hypothesis equation 2. Equation 2, we put n is equal to 0. In equation 2, we have to put n is equal to 0. We are taking here. We get the formula. What is the formula? Cauchy integral formula 1 by 2 pi integration of gamma f z by z minus z naught dz we are taking here. So we get the formula. Let's assume that n is equal to n minus 1. So that is f of m minus 1 z naught that is equal to m minus 1 factorial by 2 pi I. It is integration of gamma naught f of z by z minus z naught whole power m of dz, that is equation number 2. So in place of m, I am taking m minus 1 and m minus 1 factorial. Here m minus 1 factorial automatically z minus z naught. So m minus 1 plus 1. So therefore automatically it comes m here. Automatically it comes here, it's m here. So therefore the continuation here. So we have to prove that the formula, that the equation number 2, f of n, f power n z naught by n factorial of 2 pi, integration of gamma f z by z minus z naught and plus 1 of dz, we have to this one. So therefore I'm taking n is equal to n, I'm taking it. Let h be a sufficiently small quantity. Z plus z naught plus h belongs to I. So therefore that is gamma r. So So from third equation, we have taken a third equation that is a m, f of m minus 1 z, not m minus 1 factorial 2 pi. I am taking it that is f of m minus 1 z naught plus h minus f of m minus 1 z naught by h I am taking here. So m minus 1 factorial by 2 pi I h gamma 1 f dash f of z. So therefore I am writing here 1 by z naught h whole power m minus 1 by z naught whole power m. So what I am taking here, m minus 1 whole factorial I am taking here. That is 1 by z minus z naught h whole power m. 1 by z. So we are differentiating this one. We are writing this part here. Yeah, again, I'm writing here m minus 1 whole factorial 2 pi a h. That is integration of gamma f of z. That is z minus z naught whole power m minus z naught h whole power m by z minus z naught minus h whole power m. Z minus z naught whole power m into dz I am writing here. Provided that here, provided that modulus of h are writing z minus z naught is equal to what we are taking here t is okay. So we are writing here z minus z naught minus h is equal to t minus h. Z minus z naught minus h is equal to t minus h. So we are using the algebraic identity here a power m minus b power m. A power m minus b power m is equal to a minus b. A cube minus b cube. Formula a power m minus 1 plus a power m minus 2 into b and so on plus b power a. This is the we are a cube minus a square minus b square or a cube minus b cube. A power m minus b power m formula we are writing here. So we find that here the fundamental formula f of m minus 1 z naught plus h minus f of m minus 1 z naught. So f of m minus 1 f of z naught is plus f of m minus 1 z naught by h. We are taking here. So m minus 1 whole factorial by 2 pi m minus 1 whole factorial 2 pi integration of gamma f of z is equal to, this is a fundamental of t power m minus 1 plus t power m minus 2 into t minus h. T power m minus 3 into t power h whole square. T power m minus 4 th minus whole cube. That's why we are writing and so on. We are writing here and plus t minus h m power minus 1 by t power m by t minus h whole power m, that is into dt. We are taking here the equation number 1, 2, 3, that is 4. That is equation number 4 we are taking here. Then the right hand side of the nth term of formula f of n naught z we are writing here. Take equation 2. The right hand side I'm taking here. In a new variable new variable becomes no, new variables becomes here m factorial by 2 pi integration of gamma f of z by p of m plus 1 dz. So see here what I am writing here. So integrate m factorial, we know that here m factorial by 2 pi a integration of gamma f dot 2z plus 1 by z. Earlier equation we written here, earlier equation number 4, now the equation number 5 here we are writing here. So that so we are taking the equations of the earlier 4 and 5 we are writing here. From 4 and 5 equations, from 4 and 5 we have to get that here of m minus 1 z naught plus h minus f of m minus 1 z naught by h minus m factorial by 2 pi I integration of gamma f of z by p of m plus 1 dz. So see here, this one f of the right hand side of the new variables I'm taking, that the fourth and the fourth one and the fifth one here taking one side here. So we are writing here m minus 1 whole factorial by 2 pi I integration of gamma f of z p power m plus p power m minus 1 p minus h plus p minus h m minus 1 p minus m p minus h whole power m whole division of p m plus 1 by what p minus h whole power m. That is the condition of into p z is. So therefore we can write here f of m minus 1 of z naught plus h minus f of m minus 1 of z naught I'm writing here by r. By I'm taking the second equation in factorial by 2 pi I integration of gamma, that is f of z by gamma of sorry p of m plus 1 of dz I'm taking here. There is the equivalence to I'm writing here m minus 1 of m minus 1 whole factorial by 2 pi I. So therefore gamma of f of z I'm writing here. So the p of m plus the p of m minus 1 p minus h. So therefore plus p minus h m minus 1 into p minus m. Therefore p minus h whole power m by p of m plus 1 by p minus h whole power m. Therefore that is also is equal to d z I'm writing it. So the less than or equal to this condition here, less than or equal to condition here m minus 1 whole factorial by 2 pi I. So that's a 2 pi r m of modulus of h I'm taking here. So this is the condition what we are taking here p power m, p power m minus 1, p minus 6 plus p power m minus 2, p minus 6. So then I already told you that the simplification of that is m minus less than or equal to m minus 1, 2 pi I, 2 pi r m of modulus of h. So we are writing this one into 2r m minus 1 plus 2 into 2r m minus 1 plus 2 into 2r m minus 2, that can so on plus n into 2r m minus 1 by r minus h whole power m r into m plus 1. That is equation number, that's the equation number here. Earlier equation number 5, that is 6 we are taking here. This is the equation number 6 I am taking here. So there, this is the user estimate of this one we are taking here. This one r minus of h is equal to modulus of z minus z naught minus modulus of h, that is less than or equal to z minus z naught, we know that that is h plus modulus of h less than 2. So together with the fact that together together with the fact that t power m plus t power m minus 1 into t minus h I'm writing here, and so on plus already I told this is t power minus h whole power m minus 1 and m t minus h whole power m is equal to t power m minus t minus h whole power m. So on plus t square into t minus h whole power m minus 2 and t minus h whole power m I'm taking here. So therefore I'm writing here this one h I'm taking it a common here. T m power m minus 1, t power m minus 2 into t minus h and plus t minus h m minus 1 plus and so on plus h t minus h m minus 2 t plus t minus h plus h into t minus h m minus 1. So therefore, at least when we are taking here this one, so therefore at least also let m is equal to, so let m is equal to maximum of z belongs to gamma here, that is maximum of f of z and y. By the earlier equation, what is the sixth equation I'm giving here? By the sixth equation approaches here. Equation sixth approaches here. H tends to 0, and hence the same, and hence the same, and hence the same here is 2 of is the 2 of left hand side. The C of left hand side I'm taking here. So that is f of m of z of z naught we are taking here. The limit of x tends to 0 and limit of x tends to I'm taking here. So for f of m minus 1 z naught plus h I'm taking here minus f of m minus 1 z naught. So therefore, that is m minus 1 to m minus 1. But z plus and z naught plus h minus z naught by h we are taking here. That is n factorial by 2 pi I integration of gamma f of z by p of n plus 1 dz I am taking here. That is n factorial by 2 pi I integration of gamma f of z by z minus z naught m plus 1 into dz. So therefore, n factorial by 2 pi f of z by z minus z naught m plus 1 dz. So which is the required equation? Which is the required equation? What is the Cauchy's formula? What is the Cauchy's formula? 1 by 2 pi integration of gamma fz by z minus z naught z. Here also it is coming m factorial by 2 pi I f of z by z minus m plus 1. So m plus of 1 means what is the m plus of 1? We are taking the in the third equation also, that is m minus 1, which is the required equation, equation 11, n is equal to m. So we are taking here, this is a one fundamental analytic unit is analyzing, they are proving here. Then another theorem. The earlier theorem we have learned here, Cauchy inequality or estimate. Now we are doing Cauchy inequality or estimate. Cauchy inequality or estimate we are taking here. In the earlier theorem, G is analytic, we learned here. In that one, then let M be a positive. Let M be a positive constant such that we are taking here f of z less than or equal to m on B or alpha. Then f of n alpha less than or equal to mn factorial by Rn. This is the first equation. That's the earlier equations also. In the earlier theorem it is continuous, but here we are taking here m of n by Rn. So we are taking here the C1 is the assuming here assuming that C1 is a circle of radius its center Z0 is equal to alpha contained in G. Center Z0 is equal to alpha and contained in G. So therefore, we know that the Cauchy integral formula f of Z0 is 1 by 2 pi integration of gamma f of z by z minus Z0 dz. So therefore, we get that here contained in G here. So therefore, the equation 1 f of n alpha here n factorial by 2 pi I integration of C1 f of z dz by z minus alpha of n plus 1. So less than or equal to n factorial by 2 pi integration of C1 f of z dz by z minus alpha n plus 1. So the f of z by dz and z minus alpha simply n plus 1 also we are taking here. What we are taking here n factorial by 2 pi alpha 2 pi. We are taking the common here from the integration outside integration before integration we are taking here. So that is a less than or equal to also we can take here n factorial by 2 pi, that is m by rho of n plus 1 C1 of modulus of z we are writing here. So therefore n factorial by 2 pi m by rho of n plus 1 2 pi rho n by rho n plus 1 by 2 pi rho we are taking here. So this is the one, this is the one we are taking here, this is the one we are taking here. So we are writing here n factorial of n. The earlier one we are taking here n factorial by 2 pi and n factorial m I am taking here. That is a pn. If 2 pi get cancelled here in the earlier one. Here this is 2 pi cancelled here. What is the rho n plus 1? Rho n plus 1 here. Rho of n plus 1 here. Okay, this one. So rho of n plus 1 again rho here. This is rho. One rho will here rho of n plus rho of 1. So rho of 1 cutting here. So therefore we are writing here in the denominator part n factorial n by rho of n we are writing here. Also, this is true for rho of r. Listen out. For all rho stands to r, we get here. Modulus of f stands to alpha. Is not equal to mn factorial by r power n. This is one. This is the fundamental formula of this one. Then one example, you have to Cauchy-Hadmon inequality we have done here. Cauchy-Hadmon inequality. Cauchy-Hadmon inequality. If F is a analytic on your domain, G, then show that limit n stands to alpha, nth root of f of n does not by n factorial less than or equal to 1 by r. So this is the equation number one we are taking here. So this is the they are given example for every z not belongs to G, where R is the distance between Z naught and the boundary of G, and the boundary of G. So see here one solution here. Let R we are taking here Z minus Z naught is equal to R we are taking here. You know that the circle contained in G, contained in G. Then by Cauchy inequality, then by Cauchy inequality, f of n z naught less than or equal to n factorial by Rn. So therefore, f of n is not less than or equal to n factorial by Rn. Or we are taking here f of n z naught by n factorial less than or equal to m by Rn. So f of n z naught by n factorial also less than or equal to m by Rn. This also we have to write here. Both sides we are taking here. So that is the limiting, taking the limit of supremum of the nth root, taking the limit supremum of the nth root, supremum of the nth root we are taking here of the of the inequality. We get the results here. Limit n tends to infinity, nth under root of f of n z naught by n factorial is not equal to limit n to infinity m by Rn by 1 by m by Rn 1 by n. Limit n stands to infinity we are taking here m by 1 by n by r, that is r is equal to m by 1 by n. M power 1 by n is therefore we are writing that m power 1 by r by n is that m power naught is m power 0 is equal to 1. So m power 0 infinity I am substituting it by 1. So therefore we are writing that is 1 power r. This is the solution. Now Liebow's theorem we are learned here. Liebow's theorem. That is the definition I am writing there. Liebow's theorem. So series of the complex numbers we are taking here, sequence of the series of the real numbers, sequence of the complex numbers, series of the complex numbers. So sigma n is equal to minus 1 by 4 n plus 1 by 2n plus 1. Therefore, n is equal to 1, 2, 3 is given by 1, 2, 3, and 1 n equal 1, 2, 3 is given by we are writing here. So we are writing here this one 1 by 3 minus 1 by 5, 1 by 7 minus 1 by 8. And so on writing it minus 1 into n plus 1 by 2 n plus 1. So this is all even in our number 1 by 3, 1 by 7 minus 1 by 5, 1 by 9. Or we are taking a second one. Sigma n is equal to 1 by 3n square plus 1. Equal for n is equal to 1, 2, 3 also I am taking here 1 by 4, 1 by 13. So 3, 1 square means 3 plus 1. 2 తీసుకుంటే 2 square అంటే 4 into 3, 12 plus 1, 30. 3 తీసుకుంటే 9 square అంటే 9 and 9, 9 into 3, 40. 4 తీసుకుంటే 16, 16, 48 plus 1, 49. So 1 by 13, 1 by 28, 1 by 49, and so on the limits we are taking 1 by 3n square plus 1. So 1 by 3n square plus. So given that this one, the state values several theorems, the proof, this one, so we can take them in definition here. The following real sequence alpha n, a real sequence alpha n, is said to be convergent. Is said to be convergent if there is alpha belongs to R. So we can use the if there is alpha belongs to R, which has the some following properties we are taking here. Some of properties we are taking here. Epsilon greater than 0. There is a natural number n naught such that n greater than or equal to n naught. So that is alpha n minus alpha less than epsilon. Alpha n. Modulus of alpha n minus alpha less than epsilon. So in this case we are writing here limit instance to infinity an. We are taking here alpha or an stands to alpha as we are taking instance to infinity. Otherwise, the alpha n is equal as by reference we are taking here. Then another way again we are taking here, another definition we are taking here. The real sequence alpha n is said to be a Cauchy sequence or a fundamental sequence. We know that the Cauchy sequence or a fundamental sequence or a fundamental sequence. Each epsilon greater than 0 here. The natural number n naught such that n greater than or equal to n naught. That is alpha n minus alpha n less than epsilon. Alpha n minus alpha less than. So real sequence also. It's a real sequence also taking here. Alpha n is said to be a Cauchy sequence here. The fundamental sequence we can say epsilon greater than 0. Epsilon greater than n naught and n greater than n naught. That is also you can write alpha n minus alpha modulus alpha n minus alpha naught less than epsilon. We can write another theorem. The real sequence alpha n is convergent. You can only if it is a Cauchy sequence. If it is a Cauchy sequence. So here it is also a Cauchy sequence. If it is a Cauchy sequence. So there is another definition. And another definition, so many definitions for this one. The bounded definition of real sequence alpha n set to the bounded in the book. There is n constant n equal alpha n greater than n equal 1 to 3. So bonded MO, if there is a constant alpha and there is an n equals 1 to 3, bonded, it is bonded and above below are equality. There is a constant here, m such that alpha n is equal to 1 to 3. Every convergent real sequence is bonded. In a theorem also, the real sequence is bonded also here. Definitions also is that a real sequence alpha n is said to be the monotonic function alpha n less than or n equal 1 to 3. Monotonic decrease in alpha n greater than alpha n is equal to 1 to 3. So alpha n less than or equal to alpha n